Hi everyone. Today we're going to be completing our notes on 12.1 sequences and summation notation. I want to start just by defining what is a sequence. A sequence is a function f whose domain is the set of natural numbers. All right. So the domain are counting numbers 1, 2, 3, 4, 5, and so on. So the domain is infinite, but it's just those counting numbers. So no fractions, no irrational numbers, no roots, anything like that. No negative numbers, and not zero either. Okay? So then the terms of the sequence are the function values, f of 1, f of 2, f of 3, and so on. Okay? And this goes all the way up into f of n, where n is the nth term in the sequence, and it can continue as well. So f of n plus 1, and so on. Okay, so we can define functions in terms of the nth term of that sequence. Okay, so the sequence has terms a1, a2, a3, and so on. And this goes all the way up into an and an plus 1. And that continues as well. And so the way that we would denote this, if we just see this list of terms here, this would be the first term in the sequence. And A2 would be the second term. And then all the way up to AN would be the nth term in the sequence. Okay? So let's go ahead and try a few examples. Example 1. Find the first 5 terms and the 100th term of the sequence defined by each of the following formulas. So we'll start with an equals 2n minus 1. To find the first term, we're going to plug in 1 in for n. And so we have a1 is equal to 2 times 1 minus 1, which is equal to 2 minus 1, or 1. Plugging in 2, we get a2 equals 2 times 2 minus 1, and that is equal to 3. Plugging in 3, we have 2 times 3 minus 1, that's equal to 5. And we see this pattern continue. So A4, or A sub 4, some teachers will say, is 7, and A sub 5 is equal to 9. To find the 100th term, we plug in 100, and we get 2 times 100, and then minus 1. This is equal to 199. Okay? Letter B, here we have Cn equals n squared minus 1. So C1 is equal to 1 squared minus 1. That's equal to 0. C2 is equal to 2 squared minus 1, and that's equal to 3. C3 is 3 squared minus 1. That's equal to 8. And C4 is equal to 15. C5 is equal to 24. Okay? C100 is equal to 100 squared minus 1. Well, I know 100 squared is 10,000 minus 1 is 9,999. Okay? So to recap, the terms in this sequence in letter B would be 0, 3, 8, 15, 24, and so on. Okay? Let's try another. Letter C. Here we have T sub n equals n over the quantity n plus 3. So T1 is equal to 1 over 1 plus 3 is 1/4. T2 is equal to 2 over 2 plus 3, which is 2/5. T3 is equal to 3 over 3 plus 3. So you might be seeing a pattern here. And that's the goal for some of these sequences, that we have a pattern. Okay, this reduces to 1/2. T4 would be 4 over 4 plus 3, or 4/7. T5 would be 5 over 5 plus 3, which is 5/8. And so then T100 is equal to 100 over 103. All right. Last one on this page, here we have r sub n is equal to the quantity -1 to the power n over 2 to the power n. So r1 would be equal to -1 to the power 1 over 2 to the 1. Well, -1 to the power 1 is -1, and then 2 to the power of 1 is just 2. So we have -1/2. Plugging in 2, we get -1 squared over 2 squared. Well, this is equal to positive 1/4. We get r3 is equal to -1 to the power n over 2 cubed. So we get -1/8. R4, you might be recognizing a pattern. This is equal to positive 1/16. R5, this is equal to -1/32. Okay? R100, we'll go ahead and plug that in as well. So we have R100 is equal to -1 to the power 100 over 2 to the power 100, which is equal to, I'm not going to evaluate 2 to the 100. This is just a positive 1 over 2 to the 100. Okay, so one pattern that you might notice with this sequence here, -1/2, positive 1/4, -1/8, positive 1/16, -1/32, is that the sign keeps flipping. And that has to do with this numerator here. This factor, this term here, we can think of as like a sign flipper. It's going to change the sign of our function with each successive term in the sequence. Okay. For those odd powers, we have a negative sign. And then for those even powers, those negatives cancel out. So we have a positive sign. Furthermore, this is the negative powers of 2. So 2 to the -1, 2 to the -2, 2 to the -3, and so on. All right. Go ahead and flip the page. Let's see if we can recognize some of these patterns. All right, so example 2, find the nth term of a sequence whose first several terms are given. Letter A, 1/2, 3/4, 5/6, 7/8. Well, I noticed that the numerator, sometimes when I have these fractions here, I like to divide them up into 2 different sequences. So like the numerator here is just the sequence of odd terms, or odd natural numbers. Whereas the denominators here, 2, 4, 6, 8, are the evens. So the nth term of this sequence is just the definition of an odd and an even, the ratio. So 2n minus 1 over 2n. And you can go back and you can plug in values like 1, 2, 3, and just see if we actually do get those values. So if we plug in 1, we get 2n minus 1 is 1. Plugging in 1 here, we have 2. So yes, 1/2 is our first term. Plugging in 2, 2n minus 1 is 3. And then 2 times 2 is 4. So yes, we get 3/4. So go back and double check those first few terms and just make sure that your rule holds for that sequence. All right, for letter B, I noticed that the sign flips. So negative to positive to negative to positive to negative. So first thing I notice is that the sign flips. So we're going to use that sign flipper term or factor. And then I also noticed that the terms are just powers of 2. Okay, so it's going to be 2 to the power of n. So first, a sub n is equal to our sign flipper. The first term is negative, so we have -1 to the power of n. And then times our powers of 2, so 2 to the power n. Okay? Now I want to talk about recursively defined sequences. A recursively defined sequence is a sequence whose nth term depends on some or all of the terms preceding it. The first example is the Fibonacci sequence. Let's find the first 11 terms of the sequence defined recursively by f1 equals 1 and f2 equals 1, where fn is equal to the previous term, fn minus 1, plus the term before that, so fn minus 2. Okay, so we know that f1 is equal to 1, and we know that f2 is also equal to 1. This has been defined for us. So then f3 is equal to f2 plus f1, right? If we were to plug in 3 in for n, we'd get 3 minus 1 is 2, and 3 minus 2 is 1. So we get f2 plus f1. Well, we know what f2 and f1 are. That is 1 plus 1, which is equal to 2. Finding f4, well, that's just equal to the previous term, f3, plus the term before that, f2. And so that's equal to 2 plus 1, or 3. Let's do one more, f5. This is equal to f4 plus f3. which is equal to 3 plus 2. And so we get this sequence of terms, 1, 1, 2, 3, 5, and then 8, 13, 21, 34, 55, 89, and you can see that this just continues on and on. This is a special sequence called the Fibonacci sequence, and it's just the sequence of terms where any given term is defined as the sum of the two previous terms. Okay? But this gives us an idea for what a recursively defined sequence is. It's talking about a sequence whose definition depends on a previous term. So it could be at least one term, it could be many terms. The number of terms that the sequence is dependent on is the number of given criteria that you need, the given terms. So notice that this requires two previous terms, so we need two given terms. Okay? Example 3, find the first 5 terms of the sequence defined recursively by a1 equals 1, where an equals 3 times the previous term, an minus 1, plus 2. Well, we'll start with a1, we know is just 1. So then a2 is equal to 3 times a1 plus 2. Well, we know what a1 is, that's 1, and then plus 2. So we get 3 times 3, or 9. Finding a3, so we have 3 times the previous term, a2, plus 2. And again, we know what a2 is. It's 9. So 3 times 11 is equal to 33. a4 is equal to 3 times the previous term times the quantity of the previous term plus 2. So 3 times 35, that's equal to 105. And then finally, the fifth term is equal to 3 times 105 plus 2, which is 3 times 107, which is 321. Okay, so the terms in this sequence are 1, 9, 33, 105, 321. All right, go ahead and flip the page. Given the sequence 6, 10, 14, 18, find the following. We want an explicit definition, or just a sub n. We want the recursive definition, and then we also want the 100th term. Okay, so first thing I notice is that our first term is 6, and then we are increasing each term by a constant 4. So we are adding 4 each time. So that tells me that my explicit definition is going to be a sub n is equal to, well, think of this as like a linear function. The slope would be 4. We're adding 4 each time. Our y-intercept would be where n equals 0. So if we were to have a 0th term, then we would have to go back 4. So this would be from 6 to 2. We'll talk in our next section on arithmetic sequences, how we can define them using the first term. Okay, but this would be our general rule where the domain is a set of natural numbers. So our first term is going to be n equals 1. We're not going to include that n equals 0. For the recursively defined sequence, or the recursive definition, we have our first term. We need that given criteria. And then any term in the sequence is given by the previous term, an minus 1, and then plus our common difference of 4. So we just take the previous term and we add 4 to it to get any given term. All right. One thing to note about recursive definitions is that you require a term before it. So if I wanted to find the 10th term in a recursively defined sequence, I need to know the 9th term. And in order to know the 9th term, you need the 8th term, and so on. The explicit definition is a little bit different, where you can just plug in any value. In fact, that's what we're going to use for letter C. So a sub 100 is equal to 4 times 100 plus 2, which is equal to 402. Okay? All right, our next definition for today is a partial sum of a sequence. Okay? So I want to start just by defining, so given the sequence a1, a2, a3, and so on, all the way up to an and an minus plus 1, and that continues, the partial sums are S1 is equal to just that first term. S2 is the sum of the first two terms, so A1 plus A2. S3 is the sum of the first three terms, so A1 plus A2 plus A3. And we can continue this onward all the way up to Sn, which is the nth partial sum, is what we would say. This is equal to a1 plus a2 plus a3 plus all the way up to a sub n. And we would again call this the nth partial sum. So it's the sum of the first n terms. Okay, and so these partial sums can be defined by their term numbers. So this would be the first partial sum. Or S2 would be the second partial sum. And then all the way down to Sn would be the nth partial sum. And likewise, we can define a sequence of the partial sums as well. So S1, S2, S3, and so on, all the way up to Sn plus 1. This is the sequence of partial sum. Okay? So example 5. Find the first four partial sums and the nth partial sum of the sequence given by a sub n equals 1 over 2 to the power of n. So this is our powers of 2, but the negative powers. So we're flipping it, the reciprocals. So the terms of this sequence would be, well, the first term is the first negative power of 2. The second is 1/4, 1/8, and so on, all the way up to 1 over 2 to the power of n. Okay? So then the partial sums, S1 is just 1/2. Well, S2 is going to be 1/2 plus 1/4, the sum of the first two terms. Well, 1/2 and 1/4 gives us 3/4. S3 is the sum of the first three terms, so 1/2 plus 1/4 plus 1/8, and that's equal to 7/8. We can do one more, so S4 would be 1/2, 1/4, 1/8, and then 1/16. So this is equal to 15/16. Okay? You might be noticing a pattern with the numerators and denominators. So then the nth partial sum, well, I noticed that the numerator is always going to be one less than the denominator, and the denominator will always be that power of 2. Okay, so if the fourth partial sum is going to be 2 to the fourth. The 10th partial sum is going to be 2 to the 10th. So I know that the denominator is the nth power of 2. The numerator is the same thing, but we subtract 1. So it's that same thing as the denominator, but 1 less than that. We can also split this up and say that this is 1 minus 1 over 2 to the power of n. Either of these answers are acceptable. Okay? All right, go ahead and flip the page. We got just the last thing for today. We'll talk about summation notation. Another name for this notation is sigma notation. And the reason why we call this sigma notation is because that the notation that we use to denote this is the capital Greek letter sigma. And so that represents the sum of the first number of terms. Okay? So let's go ahead and define this. Given the sequence A1, A2, A3, and so on, all the way up to AN, the sum of the first n terms is denoted by, we have this sigma notation here. So this is the capital Greek letter sigma. Looks like this. And this is denoted as, on the bottom of sigma, we're going to say k equals 1. And then on the top of sigma, we're going to say n. Okay, so this is just saying this is the sum of terms from 1 to n. So from the bottom to the top. And then we would define this as a k, where we have the index k, is equal to the sum of a1, a2, a3, all the way up to an. Okay, so this is the sum of the first n terms. So we can shorthand this. Instead of writing a1 plus a2 plus a3 plus a4 and so on, we can just shorthand using the sigma notation. Okay, so these mean the same thing. So let's go ahead and define these. So where k is the index of summation. Or another way we can define k is it's the summation variable. Okay. So the way that we can evaluate some of these sigma notations or summation notations is we can replace k with integers. Really, it should be natural numbers from 1 to n. And then we just take the sum. The reason why I say integers here is because we're going to use sigma notation for things beyond just sequences and series. You'll learn in calculus, we use sigma notation to define integrals, right? And so we're going to be using terms outside of the natural numbers. So we use integers with all of sigma notation, but just for our intents and purposes for sequences and series, we're just going to be using natural numbers, so from 1 to n. Okay? So let's go ahead and find each sum. So this is saying find the sum from 1 to 5 of k squared. Okay, so this is equal to plugging in 1, and then 2, and then 3, and then 4, and then 5, and then we're going to add all of those up. So we're just squaring the input. So this is equal to 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Okay, well, this is equal to 1 plus 4 plus 9 plus 16 plus 25, which is equal to 55. Okay, so this is the sum of the first terms of the sequence k squared from 1 to 5. Now we've got our reciprocal, 1 over j. So this is equal to, we're just going from 3 to 5. So we're starting with 1/3 plus 1/4, and then our last term is 1/5. 1/3 plus 1/4 plus 1/5 is 47/60. Okay. Letter C. Now we've changed our index to I, and so we're finding the first 5 terms from 5 to 10. So we have 5 plus 6 plus 7 plus 8 plus 9 plus 10. Okay, so this is equal to 45. And then letter D, well, we don't have an I here in this expression, so this is just equal to the first 6 terms of just the constant 2. So this is equal to just 12. Okay, so there's no variable to plug in here. All right, let's practice rewriting using summation notation. So see if you can recognize the pattern and come up with a rule. So I noticed that in letter A, we have our powers of our perfect squares. However, we're starting with 2 squared, okay? And then we're going all the way up to 256, which I know is the perfect square of 16. If I were to rewrite this as perfect squares, this would be 2 squared plus 3 squared plus 4 squared plus 5 squared, all the way up to 16 squared. And so we can write this using sigma notation from k equals 2. We're starting with the perfect square of 2, all the way up to 16 of k squared. Okay. For letter B, I noticed that we have 1, 3, 5. I would expect the next to be 7, square root of 7, all the way up to the square root of 23. Okay. So that tells me that these are all our square roots of odd numbers. 1, 3, 5, 7, 9, 11, 13, and so on, all the way up to 23. So we have the sum of from k to, well, let's figure this out. I know that this, if we were to define our odd numbers as 2n minus 1, but now we're going to use the index, the summation index, 2k minus 1. It's the square root of those. Well, for what value of k gives us 23 in this expression? 2 times what number minus 1 is 23? The answer, 12. 2 times 12 minus 1. So then our summation is the sum of terms from 1 to 12 of the square root of 2k minus 1. Okay? So these have been our notes on sequences and summation notation. We talked the explicit formula, we talked recursive formula, we talked partial sums, and we also talked summation or sigma notation. We're going to get a lot of practice in class, so we'll see you tomorrow. Goodbye, everybody.